All right, so the plan for today is to finish up section 3.2, and if we have time, start section 3.3 on measures of position, wrapping up chapter 3. I'm sure we won't finish 3.3 today, so we'll leave that till next time to finish, but we should, we might get us started it, but we should at least finish up 3.2 today. There are a couple supplements posted on Blackboard under the supplemental materials folder. There's a chapter 3 subfolder. One of them is on, well, two of the supplements. One, kind of explanatory document, and one set of answers to that is on 3.3. So when we talk about percentiles, we'll talk about how to compute percentiles and so on using a more graphical approach rather than the more algorithmic approach that's in the book. And so those two documents are just a little bit more information on that, a little bit more practice on that. Then there's also a document called Y divide by n-1. And you'll see that when we compute variance and standard deviation, we end up dividing by n-1 instead of n. That has to do with reducing bias or making an unbiased estimator. And this document is just kind of a supplement to walk you through an example that demonstrates why we divide by n-1 instead of n. So that's kind of beyond the scope of this course, why we do that. And a full proof is definitely beyond the scope of this course. But this at least gives you a little bit of a demo of the problems that might occur if we divided by n instead of n-1 in the variance and standard deviation. Seems very strange to do that, but that's what we have to do to get an unbiased estimator. And also, as I mentioned last time, and I think I sent out an announcement as well, there's a supplemental video on the YouTube playlist on the geometric and harmonic means. So I think that should have been, it should be at the top of that playlist. I had to go in and like manually reorder it. So if that manual reordering stuck, it should be at the top of the playlist on YouTube, or maybe, Monday's class might be above it, but it should be near the top anyway. Yeah, so definitely take a look at that supplement. It's less than 20 minutes long, 17, 18 minutes long, something like that, and introduces you to these two other means that are important in different contexts, but we skipped over just for time considerations. Okay, so returning to measures of variation, we have the data sets that we've been using, same old data sets. And we had discussed previously the range. Remember, the idea of measures of variation is to answer a question that's something like, how variable is the data set? How spread out is the data set? Something like that. And one attempt at answering this question was the range. We just take the maximum data value minus the minimum data value, and that gives us a measure of variation. The more spread out the data is, the wider the swath of the real line we presume it will cover. The pros to this were that it's easy to compute. It's a pretty easy thing to compute by hand. 100 minus 25, I can see right away that is my range 75, or I can find the range very quickly for most data sets. If I had 10,000 data points, it might be a bit of a pain to find the max and min, but much less of a pain than really anything else I would need to compute on that. It's also simple to understand. If I tell you this is how the range is computed and tell you what the number is for a certain data set, even without taking a whole stats course or anything, you probably kind of understand what it's saying. It's the swath of the real line that the data covers, the size of that interval. The con, though, maybe at least one con, but for the biggest con, is if I have a data set of size 10,000, the range only looks at 2 data points. If I have a data set of size 2, the range looks at 2 data points. Regardless of how much data I have, the range only considers the extremes. Can I come up with a measure of variation that does something that I would expect a measure of variation to do, that gets larger, that reports a larger number when the data set tends to be more variable, but that kind of like investigates every data point? Right, kind of roughly speaking, I would like to be able to tell the difference between a data set that looks like this, right? If I have 100 data points that are all right in the middle, and then one data point that's kind of off to the left, and one data point that's kind of off to the right, I mean, this isn't all that volatile of a system. Like most of the time, if I randomly pick somebody from this system, they're going to be right in that middle. Versus if I have 50 or 51 or whatever at each end here. Well, now it's like it's basically a coin flip. It's in a sense like almost as random as it could get. Like I might get a really high number or I might get a really low number if I pick one person at random from this population. The range would be the same because the size of the swath of the real line that the data covers is the same, but you know, clearly it seems that this would be lower variation and this would be higher variation. The chance that I get something wildly different from what I expect is much higher in the second example than in the first. Right, in the first, every once in a great while, I get something that's quite far from what I expect, but most of the time I get basically exactly what I expect. In the second one, I'm always getting something that's far away from, you know, where the average would be somewhere right, right in the middle here. Okay, so the variance is our attempt to answer this question, to come up with a measure of variation, something that gets a number that gets larger whenever our data is kind of roughly speaking more spread out, but that also investigates every data point instead of relying on just a couple of them at the extremes. Now, one thing that we might notice is if our data set is more spread out, the mean, we know the average is a measure of center. It's kind of like, roughly speaking, the middle of the data set. So if the average is like the middle of the data set, I can take that as kind of an anchor, like it's like a flag set in the ground. And I can kind of measure how far away each data point is from that mean. If I tend to have lots of data points quite far away from the mean, I would think that that would probably mean that my data set is pretty spread out and might have a higher amount of variation. Maybe the number I want to report from that is a higher number relative to a data set where most of my data points stay pretty close to the mean. Since the mean is kind of the middle of the data, I think that the farther the data points tend to be away from the mean, the more spread out the data. So what might I do? I might take, let's say, a data set that has this mean. And maybe it's a data set of, say, size 10. I'm going to write 10 dots on here. I'm going to write them kind of vertically, kind of disjoint from one another, not for any particular reason, but just so that I can draw something else a little bit later on. So here's 10 data points. This X bar might be, we say roughly the mean for these. Again, the vertical distance isn't for any particular reason. I want to be able to draw horizontal bars. I don't want them all running into one another. That's the only reason. So this is like X1 would be this value, X2 this value, X3, X4, and so on to X9 and X10. I would like to investigate each data point, say the data point X sub I, and I'm interested in how far it is away from the mean. If it tends to be the case that lots of my data points are really far away from the mean, that data set is pretty spread out. I'd want to report a high number for the variance. If it tends to be the case that most of my data points are pretty close to the mean, then I want to report a low variance, right? Here, most of my data points, or really all of my data points, are quite far away from the mean. I want a high variance. Here, most of my data points are really close to the mean. I want a low variance. There are a couple that are outliers out here, but most of them are pretty close to the mean. I'd expect a lower variance up here. So I might look at a measurement like this, like xi minus x bar, kind of a distance away from the mean. So I might be interested in this distance, say x10 minus x bar, this one, x9 minus x bar, and so on. And what do I want to do with these distances? Again, because I want every data point to contribute, I don't want to take like the max distance or something like that, because then I'm only looking at really one data point. Maybe I'll do something like just add up these distances. So I might take like x1 minus x bar plus x2 minus x bar and so on, plus xn minus x bar. So I add up these xi minus x bars. This almost works. There's a little bit of a problem here, though. On the right-hand side, when the xi's are bigger than the x bars, these are positive numbers. On the left-hand side, though, say x2 minus x bar, if I have a number like 1 minus 10, well, that's actually a negative number, as is, say, x3 minus x bar, and so on. These ones on the left, these quote distances, if I just do xi minus x bar, it's not really a distance. It's like a signed distance. And in fact, I have cancellation, right? I have a bunch of negative numbers on the left, a bunch of positive numbers on the right. I add them together and I get a lot of cancellation. In fact, I get perfect cancellation. If I add all of these up, well, I can get rid of my parentheses, collect my xi's, and then I have minus nx bars. But what is nx bar? X bar is the sum of x1 through xn over n. This is exactly equal to 0. So I have something that kind of seems like it's along the right track, but if I leave it as is, the measure is always 0. So clearly that's not doing what we want it to do. But I want something with the feel of this. Well, one thing that I might think of doing is just actually taking the distance. What I said I was going to do in the first place, but kind of messed up a little bit. If I just take, say, absolute value of xi minus x bar, the positive numbers on the right stay positive, but these negative numbers on the left jump positive. So now I have, absolute values here. So something along these lines. This would, with a minor adjustment or two, this would actually be a good measure of variation. And in fact, this has a name. It's the MAD. Depending on the context, maybe the mean absolute deviation or the median absolute deviation, again, with a couple minor changes to this idea. But there are two things that make me cautious about going this route. The first is that, and this is a bit of a minor consideration, but the first is that absolute value is kind of an annoying function to deal with. It has this corner, and it turns out that kind of a function having a corner in it kind of causes some problems here and there occasionally. I don't think that's particularly a good reason to avoid a function because it makes the math a little messy. But it's one reason, right? It makes the math a little bit messy in some contexts, having a corner like that. The absolute value is also a piecewise function. That's a little bit annoying to deal with. So, on one hand, it's a minorly annoying function to deal with. Let me undo all of these absolute values for now before I get to the point where I can't undo them easily. Okay. So why not do the absolute value? Well, it has this corner, minorly annoying. It's a piecewise function, minorly annoying. The bigger reason that we might want to avoid an absolute value is if we remember when we were looking at our measures of center, particularly x bar is one of our measures of center. We said they all kind of naturally derived from this underlying concept with this like loss function kind of idea. And the loss function that looked like absolute value of some stuff was really associated with the median. Whereas the loss function that was like stuff squared was associated with the mean. So the mean is kind of inherently tied to the idea of squaring something, not absolute valuing something. And that's probably the more fundamental reason that I'm hesitant to use the absolute value. It's almost like, I'm trying to convey an idea in one paragraph, and I say the first sentence in the paragraph in English, and I say the second sentence of the paragraph in French. It's like, wait, you're talking two different languages here. If we throw absolute values on this guy, we're kind of talking the mean language that has to do with this like squared loss function. But then we're throwing absolute values on it that has to more to do with the median than the mean. So we don't want to use absolute values, even though, again, using absolute values with a couple minor modifications, say like using the median instead of the mean, would probably be a very reasonable measure of variation. It's not one we're going to discuss, but it would be a reasonable one. So back to our inherent problem, some of these parentheses are negative, some are positive. We add them together, they cancel out. Our problem is that we need to make them all positive or non-negative. I can also do that by squaring. If I choose to square everything, the square of a positive stays positive. Let's see, squared. But the square of a negative is positive. So by squaring everything, I make everything positive or non-negative, positive or zero. And then I add them all together. I'm adding a whole bunch of positive numbers together. Now I do have something that's starting to feel a little better. This squared is also kind of concordant with the X bar that's in there that we're using as our kind of stake in the ground for the middle of the data. So that's also a nice feature. I do have a little bit of a problem here. If I think back to what really my goal is, I have a population, let's say people in Pittsburgh, I want to know the heights of people in Pittsburgh. That population inherently has a variance and it inherently has an amount of tendency to deviate from the mean. Some people are a bit taller, some people are a bit shorter in terms of the whole population. I take a sample, maybe I take a sample of size 100. I want to estimate the population variance off of my sample variance. That's kind of my goal, right? I would like to have the population variance. If I knew that, I would basically just be done and I'd forget about all the sample stuff, but I don't have access to the population. I'm stuck using a sample. I want to compute the sample variance to estimate the population variance. Well, if I have a sample of size 100, I'm adding 100 of these things together. That's going to give me some estimate of the variance. If I take a bigger sample, say size 1,000, now I'm adding 1,000 non-negative things together. Almost certainly the variance for the sample of size 1,000 is going to be bigger than the variance for the sample of size 100 if I computed it this way. Or if I take a sample of size 900,000, it's just going to keep getting bigger the larger the sample I take. So because I'm adding together n positive or potentially zero, but essentially always positive things, the larger the sample I take, if I computed it this way, the larger the output would be. So this would be as much a measure of the size of the sample as it is a measure of the inherent variation in the population. So what do I want to do? Well, I want to scale out the size of the sample. So I'm looking for the average square deviation from the mean. So that's what our variance is. Roughly speaking, it is the average square deviation from the mean. That's our variance. Now our variance is important enough, it gets a standard notation. So it has, just like the mean, it has a population notation. Its population notation looks like this. Importantly, this is a notation. It's not a set of mathematical symbols. This set of pixels on the screen is a notation. This notation is using the Greek letter sigma. This is the Greek lowercase s, one of the two Greek lowercase s's. You might be familiar with the Greek capital S. The Greek capital sigma we use for things like summations. You see this in the book quite a bit. I try to avoid using this because I think it just throws another piece of throws more confusion into the mix. And the other Greek lowercase sigma looks like this. It's the sigma that comes at the end of the line, and that's of course where we get RS from. RS doesn't look like this one, it looks more like that one. But this is our Greek lowercase sigma that occurs in the middle of the word. And that's what we see here with a superscript 2. That denotes our population variance. Now, since we're in the context of a population, instead of calling the mean x bar, I'm going to call it mu. And that's my calculation for the population variance. There's a lot going on here, but again, we're going to go through a couple examples. We're going to take it slowly. And, the first couple of times you go to compute this, it's going to be really confusing and complicated. The next couple of times it'll go a little smoother. By the 10th time that you do, a practice problem or problems in the homework or whatever, it'll be pretty straightforward to go through the steps. So this is my population variance. I also have a sample variance, which we denote S squared, S with a superscript 2. Again, the kind of, American or English or whatever Roman equivalent of sigma. And it looks very similar. Starts off very similar. We have x1 minus. Now, since we're in a sample, I'm going to call the mean x bar instead of mu, so x bar. So I still in my numerator have the sum of the squared deviations from the mean. In my denominator, though, I end up having to divide by n minus 1. Again, you might ask, why do we need to divide by n minus 1? The short answer is to create an unbiased estimator. So that if I have my population, if I take a sample, compute its sample variance, I take another sample, compute its sample variance, I take another sample, and I do that a bunch of times, and I average together all the sample variances, kind of on average, they will match the population variance. That's what it means to be unbiased. If I were to divide by n instead of n minus 1 in my sample variance, this would not be true. Now you could ask again, why? Why would it not be true? Well, that's the demonstration that I've posted in the chapter 3 subfolder of the supplemental material folder. So that's a demonstration of why it's not true for a particular case, why it doesn't work one way and why it does work this way. And like I said, the general proof for why this ought to be true in general for any sample applied to any population is beyond the scope of the course. But if you were really interested, you could look up, sample variance or something on or like bias of sample variance. There's, I can't remember whose name it is, but it's somebody's correction to the sample variance, like Cauchy's correction or Chebyshev's correction or something. And you can find on Wikipedia the proof, or in any good mathematical statistics book, the proof for this in general. But like I said, that's well beyond the scope of this course. So our population variance, our sample variance computed essentially the same way, right? It's both of them have the same field of them. It's something like an average squared deviation from the mean, but we just have this little correction of n minus 1 in the denominator instead of n for the sample variance. And before we do any computations on this, we're going to jump to the standard deviation, because the standard deviation is very closely related to the sample variance. We're going to see the need for this in just a minute, but the standard deviation also has a population and a sample notation. And my population standard deviation is sigma. And it's the square root of sigma squared. It's the square root of the population variance. And my sample variance I denote by just S. It's the square root of S squared. It is the square root of the sample variance. All right, let's look at a couple examples. So let's come up here and grab the Ashley data first. Keep in mind that these data are a population and they're in units of returns per day. Okay, so let's look at our Ashley data. So in order, they are 5, 7, 8, 9, 11. We know that the mean for the Ashley data was 8 returns per day. So we know the mean was 8 returns per day. Our goal is to compute the variance in the standard deviation. So let's compute the population variance for the Ashley data just based on this formula here. So sigma squared for the Ashley data. Okay, I see for the Ashley data that n is 5. There are 5 data points. And I know that for each data point, I want to do xi minus mu all squared. So I want to start with my first data point 5, subtract the mean of 8 all squared. Oops. Okay, so this is what I want to do. Let me do one step where I just simplify the subtractions. 5 minus 8 is -3. That's squared. Plus 7 minus 8 is -1 squared. Plus 0 squared. 9 minus 8 is 1 squared. And 11 minus 8 is 3 squared. Remember, when I square a negative, that turns into a positive. So -3 squared is 9. Plus 1 plus 0 plus 1 plus 9 over 5. Or this gives me 20 over 5, or 4. So the variance for Ashley is 4. Okay, that wasn't too terrible, but these were, number one, pretty easy numbers to deal with. They weren't large numbers. They didn't have decimal points or anything like that. And number two, there were only 5 of them. If this was a bigger data set, I would want to be a little more organized about things. So let's take a look at the Brandon data. We could do the Brandon data the same way. It's, again, small enough number of data points and simple enough structure to the numbers that we wouldn't have a big problem here. But let's look at a way that's going to generalize a little bit better to slightly larger data sets to slightly messier numbers. Well, one thing I might want to do is start kind of like I did in chapter 2 by organizing my data, by putting it into kind of a chart. So I'm going to start by writing a column for I and a column for xi. I is just going to be my index column. So x1 is 3, x2 is 5, x3 is 7, x4 is 11, and x5, 14. Now, one thing I can see is that by organizing my data this way, I can actually get a lot of my measures of center very quickly. For instance, I see that my sum is going to be 40, and therefore mu for Brandon is going to be 40 over 5 is 8 returns per day. And I can build off of this table, right? I could pretty easily find, say, a median or a mid-range, right? I can even find a mode pretty quickly for a small number of data points. I could look down and just see in order. I can just count them up and see which one occurs most frequently. But I could continue building off of this to build up my, well, let me actually just copy it down here. Let's see. Can I copy this? Let's see if this will copy down. Okay, that worked a lot better than I was expecting. Microsoft, you never know when you move stuff around. Sometimes it like destroys the whole document and sometimes it works just right. So this time it worked just right. But okay, so I want to keep building this up. I have my xi's. The next thing that I need, and I have mu, which I just calculated. The next thing I need is my differences, xi minus mu. Let me actually just make a column for that. I'm just appending a column onto my data set. This I would call kind of like my data set, and I'm just sticking another column onto it. So I just take, for instance, 3 minus 8 is -5. Or 5 minus 8, -3. 7 minus 8, -1. 11 minus 8, +3. 14 minus 8, +6. Now, one thing I notice here is that this sum, well, this was just the sum of the xi minus mu's. That should be 0, right? I can actually check this. 5, 8, 9 to the negative, and 3 plus 6 is 9 to the positive. The sum is 0. That checks out. So I could actually check this sum of this column and make sure it sums to 0, or at least pretty close to 0. I might get a little bit of rounding error. Maybe the sum is like +1 or -1 or something if I have more numbers or if I had to round some of them. But the sum should be close to 0, and it is. What's the next operation I have to do? I need to take each of these and square them. So I take -5 squared, and then that gives me 25. -3 squared gives me +9, -1 squared 1, 3 squared 9, 6 squared 36. So it looks like I get what? So this is 10. So I have 35 plus 36 is 71 plus 9 is 80. And what does this sum represent? It represents the entire numerator. It represents the sum of the squared deviations from the mean. Sometimes we actually call this the SSD, sum of squared deviations from the mean. But it's the numerator in this big fraction. And then sigma squared for Brandon is 80. Again, this is a population, so we're just dividing by n, not n minus 1. 80 divided by 5 is 16. So setting up this chart takes a few extra seconds on the front end, but number one, setting up the table in the first place actually makes it easier and quicker and probably a bit less error prone too to compute our measures of center. We kind of have to rewrite the data most of the time anyway so that it's in increasing order. So we're not losing a whole lot of time. Things are organized. And then in this section, we can build off of this chart to help us compute our variance. So Brandon's variance is 16, Ashley's variance 4. Now, this looks like a reasonable measure of variation. I might look at this and say, okay, I mean, similar context, similar units. Maybe Brandon's data is about 4 times as variable as Ashley's because 16 is 4 times as big as 4. I want to be a little bit careful here, though. What are my units on these variances? We don't want to just jump in and write 16 returns per day and 4 returns per day. Let's check the units. Well, this column is in returns per day, as is the mean. If I take their difference, I get returns per day. So like this number is say -5 returns per day, or this number is +6 returns per day. But then I square them. When I square a number that has a unit, the number gets squared, but also the unit gets squared. This column is actually in returns per day squared. This isn't a very sensible unit, right? Even if it was like inches to inches squared, we say, okay, I know what a square inch is. Maybe it's like a measurement of area instead of linear distance, but still relative to linear distance, a square inch doesn't really make sense. When I add these up, this 80 is in returns per day squared. When I divide by 5, 5 is just a counting number. It is unitless. So my variance is in returns per day squared. This makes the variance very difficult to interpret. And as an aside, the same thing is true, of course, of Ashley's data. It is in returns per day squared. So if I'm looking for a numerical descriptive measure of the data, if I report the variance, it's really difficult to interpret because it's in a funky unit. It's in a unit that I don't even know what it means. It doesn't make any sense. So I have this issue with units here. Now, as an aside, the variance has nicer mathematical properties than the standard deviation. So we do use the variance quite a bit because of its nice math properties. But when we report a number that we want to use to interpret or to understand the data set, and the variance maybe isn't the best choice. But how do I get rid of this square unit? Well, that's where the standard deviation comes into play. If I square root everything, So what is Ashley's standard deviation? It's the square root of 4, but not just 4 returns per day squared. This gives me 2, and my unit now is back to returns per day, a unit that I understand and am familiar with in the context of this data set. So if I'm going to report a number as a descriptive measure of the variation of a data set, probably going to go with the standard deviation over the variance because of that consistent units issue. If I want to work with something mathematically, it might be nicer to say prove a theorem in the variance or something like that. Maybe the math works a little nicer over there, and I'll leave my interpretation. If I need to interpret something or understand something, I'll switch to the variant or the standard deviation when needed. Similarly down here, what's the standard deviation for Brandon? It's the square root of 16 returns per day squared. It's 4 is the number, and the unit we've recovered returns per day. So like I said, a lot of moving pieces, a lot of stuff going on here. But after you do this a handful of times, it gets easier. Okay, let's bring down our salary data. Okay, so I have my salaries here. The first thing I'm going to do is sort them in increasing order. So I see I have 28 or 25, 3 28s, 30, 55, and 100. I can really quickly say find my median. I can find my mean by adding up this column. I see there are 3 28, so I'll just do 3 times 28. And that gives me 294. And I divide by 7 to get my mean of 42. X bar is 42. So again, what's my formula for sample variance? It starts out very similar. Maybe I'll actually copy it down as well and cross my fingers again that everything copies nicely. Can I fit it here? Okay, good. Okay. So the setup for the numerators is exactly the same. I need to get my deviation of each data point from the mean. I need to square each of those and then add them together. The only difference is this very last step here where I decide what to divide by. I have to divide by a different number, not n, but n minus 1. But the rest of this chart is the same, whether we're in a population or a sample. So I make another column for xi minus x bar, 25 minus 42. And I think that's 17, but with a negative. I have these in increasing order, so I actually know that if I go up 3 on my xi, I get 3 units closer to 42, so this should be negative 14. The number 4 comes up so often, and OneNote just loves to make my 4s into 9s. I should start doing like the 4 that looks like that or something, but I don't know, it just never looked right to me for some reason. I see 3 copies of 28. So negative 14 for each of those. We go up to 30, we're 2 closer. So to negative 12. 55, I'm on the other side of 42. 55 minus 42 is positive 13. And 100 minus 42 is just shy of 60. It is 58. Again, if I wanted to do a quick check, the sum on the positive side, I have 68 plus 3 is 72. And then minus, what do I have? 10, 20, 30, 40, 50. 4 threes are 12, 14, 21. Did I add something wrong? Yes, I did. 71 and minus 71 is 0. So I've kind of confirmed that everything looks good. My sum of the deviations from the mean, not the square deviation, sums to 0 as I expect from our discussion before. So now I have all of these components, the insides of the parentheses. Next, I need to square them and add them together, and that gets me my numerator. So I have, for instance, negative 17 squared. Of course, I could just do 17 squared. I know the negative is going to square off. That gives me 289. Fourteen squared, 196. And I have 3 copies of that. I have 3 copies. I write it down 3 times. I don't like, for some reason, skip over the repetitions. These represent 3 distinct people who happen to have the same salary. So I write it down 3 times. 12 squared, 144. 13 squared, 169. And 58 squared will come over here for that one. 3364. I even tried really hard not to make it do that this time. Okay, so this gets me all of the squares, and now I need to add them up. So let's add them up. So I have 289 plus, oops, 289 plus, I have 3 lots of 196. I might as well do 3 times 196. That's fine to do. Plus 144 plus 169 plus 3364. Does that look right? Looks good. This gives me 4554. I actually realize that this 3364 contributes something like 3/4 of the contribution to the variance, even though it's just 1 out of 7 data points. We'll discuss in a minute the effect of outliers on variance standard deviation. Remember, this is one where we thought there's probably some right skewedness here. We think this 100 maybe is an outlier. Again, a little bit subjective at this point, but we see this outlier contributing 3/4, 3,300 on 4,500, 3/4 of the effect on the variance. It's clearly a much larger number than any of the other ones in this column. Okay, so my variance for the salary data, I'll write it as S squared because it's a sample variance. This is my numerator. This is my sum of square deviations from the mean. 4554. And then importantly, over n minus 1, when I draw my, or when I write out my data points in this manner, I see that n is 7. I can figure out n right away also, that just by listing the indices. And n minus 1 then is 6. Why do we do n minus 1 instead of n? Again, you can look at the document. The short answer is estimator bias. We want an unbiased estimator. The slightly longer answer is in that demo in the document. The full answer is beyond the scope of the course. But if you wanted to look it up, you could find the details in any number of places online. Or if you're interested, if you want to pop in office hours or something, I can point you to a resource. Okay, so 4554 over 6. Let's come over here, divide by 6, 759. And keep in mind, just like before, this is a number that carries square units. The original data was in thousands of dollars. This is in thousands of dollars squared. I guess I can square 1,000. I mean, it's just a million, but like, what is a square dollar? If you handed me a bill that was a square dollar, I probably wouldn't accept it. I would think it's counterfeit. I don't know. Maybe that's like fruit bucks or something, right? If any of you watch The Office. Okay, so again, I have my sample variance here for the salary data, 759 square thousands of dollars. I don't really know what that means. If I want something that I can interpret, I report the sample standard deviation, which I denote S, and it is the square root 759 1,000 square dollars, or that's the square root of 759. I can come over to my calculator and just do second square root. I could type in 759, or I could do second negative sign where it says answer. That'll just pop in the previous answer. So if my previous answer was a messier number, I might just want to do this. 759 isn't too bad to type in, but if I wanted to type in the previous answer and it was kind of an annoying number to type in, I could just do this. Gives me about 27.5. And importantly, that is back into the units of the original data, thousands of dollars. So my sample standard deviation, about $27,500. And I can, view that in the context of, say, my mean, which was in that same unit, my original data, which was in that same unit, right? All my other measures of center, my range, I can view this in the context of all of those other measures and numbers because now they have consistent units. Any questions on this?
I have a question.
Sure, yeah.
For the N-1 for the salaries, how come we used N-1 down here instead of throughout the other problems for like the one for like Ashley and Brandon?
Yeah, because this one is a sample. And Ashley and Brandon, I guess I didn't bring those down, but these are both populations.
Okay, it makes sense now. Thank you.
Yeah, yeah. Yeah, that was yeah, I should have brought that down with the Ashley and Brandon data, but these are populations. There would be no way if I just said, here are the 5 numbers, go at it. You wouldn't, there's no way to tell whether this represents a population or a sample. So you'd have to be told, this is a population, or asked, find the population variance and standard deviation, something like that. Yeah, but once we know it's a population versus a sample, we use the N-1 in the denominator, population N. Any other questions? Okay, so again, it's a good bit of calculation. There's a decent bit of work to do. On the plus side, this is probably about the most, calculation or computation intensive part of the course, I would say. Anything more computationally intensive than this, like say calculating a regression line, we're gonna just use Excel for. We'll never do one of those by hand. It's just really too much calculation. As I mentioned before, when you're in the measure the center section, and if you get, a data size of, 10 to 15, maybe even 20, if the numbers are fairly nice like this, like these, or like the Ashley and Brandon data where you can add them together pretty easily, I would do those by hand for, say, a mean or a median or something. if you get above a data set of size 20, or if you get a data set of size, say, bigger than 10, and the numbers aren't nice, if they're like a bunch of decimal points or really big numbers, maybe use Excel for those. For this section, for variance and standard deviation, I would set the bar at about like half of that. For not so nice numbers, if you get, say, more than 5 data points and you need to compute a variance or a standard deviation, I would jump over to Excel. And if you get nicer numbers like these Ashley Brandon data or the salary data, nicer numbers, you know, maybe up to size to a data set of size 10 or so you could do by hand. But you can see even with a data set of size 7, where we had repeated data, which made it easier that we could, just copy some of these down. It still was a bit cumbersome. So once you hit, data set of size 7 to 10 or so, that's about where I would start looking at the cost benefit of switching to Excel. On one hand, you have to grab the data, open Excel, put it in Excel, get it, set up the way that you like, use the Excel formulas and so on. So there's a bit of cost to doing that. And I think the benefit significantly outweighs the cost, both in terms of the time and effort, but also in terms of the learning. Once you hit that barrier of maybe something like 7 to 10 or so on a variance or standard deviation, even with nice numbers. Once you get up to a certain point, if you were trying to compute the variance of a data set of size 50, like, you're probably going to make a mistake. I would make a mistake. It's probably going to be a dumb mistake where you left a number out when you were adding them up or something, because there's just so many numbers to add up. And that's not really, you're not really learning anything there. It's just making goofy mistakes and trying to find which number you left out of this huge sum or something. Then you're not really learning statistics or understanding the material. Okay, so we have variance and standard deviation, these two new ideas, these two new measures of variation. And we do see that it appears that outliers affect the variance and the standard deviation, right? We saw that Brandon's kind of bad day and good day had what at least kind of seems to be a disproportionate effect on that numerator, on the variance, relative to his kind of typical days. And that's a product of this squaring function, right? X squared, the output gets bigger relative to the input pretty quickly, right? If I double the size of the input, I quadruple the size of the output, right? So 2x squared equals 4x squared. So for variance and standard deviation, they're disproportionately affected by outliers. This is actually going to be a pretty important idea throughout the course, really. So outliers have a disproportionately large effect on variance and standard deviation. It's not like if you have an outlier that's like twice as far away from the typical data value as another value, that its effect on variance is going to be twice as large. It's maybe going to be something closer to 4 times as large for variance. Now that does scale back a little bit whenever we come back to standard deviation, because we're square rooting things. But note that the effect size is still kind of maintained throughout. So the effect size is still, somewhat disproportionate. Okay, so that was kind of the big idea in section 3.2 is variance and standard deviation. All these ideas related to them, how to calculate them, the estimator bias bit, the inconsistent units bit with the variance and why we need the standard deviation. these were all really the most important ideas in this section. But we also have a handful of kind of ancillary ideas that we want to discuss. Oh, and before I start on that, let's jump over to Excel and actually compute these things in Excel. The range, variance, and standard deviation. So we have our same data sets, the Ashley, Brandon, and salary data. The salary data is fixed, so if you're using the revised Excel file, that's fixed. And let me actually shrink this down just a little bit so we can get everything on the screen. And let's go through and compute the range, the variance, and the standard deviation for each of these data sets. So the range we know is the maximum data value minus the minimum data value. We don't have a built-in Excel function for that, but we can just use max minus min. So equals, to tell Excel I want to compute something, max, I want the maximum of this data, which I just select. I close the parentheses. And if I just stopped here, that would give me 11, the maximum of the data. But I want to do max minus min. So min, open parentheses, select the data, and close. I see that gives me 11 minus 5, 6. That's just what I expect. If I want to, I can actually just click and drag on this bottom corner here over to the right. And I double click and see that that actually has moved all of this over 1, max of the Brandon data minus min of the Brandon data, C2 to C6 for his data set, giving us a range of 11. And for salary, I could choose to do max of, start typing in salary. There it is. I hit tab to enter it and end parentheses. And then I can do minus min of salary. Again, tab to enter salary in once it's selected. So max of salary minus min of salary is $75,000. 100 minus 25 in units of thousands of dollars. The variance. So the Excel function for variance is equals VAR. And you'll notice that when we start typing in VAR, there's a bunch of different choices. There are these deprecated ones, these ones with a little kind of triangle yield, like exclamation point symbol on it, whatever. Those are old ones, VAR and VARP. The new ones, they have these more, Java-y feeling VAR.P and VAR.S. So these days, everything is like main idea dot sub idea, and they've kind of transitioned to this. I see that Ashley and Brandon are populations. VAR.P calculates variance based on the entire population versus VAR.S, if we select that one, estimates variance based on a sample. Ashley and Brandon are populations, so I want to use VAR.P. I can either just double click on it, or I can type in VAR.P, just, the period and then P. I can select my Ashley data, and I see I get a variance of 4, matching with what we saw when we did it by hand. Similarly with Brandon, equals VAR.P of, and I start typing in Brandon. There it is. It comes up, it's selected. I hit tab. I close the parentheses, hit enter. Brandon's variance is 16. Keep in mind, these are in strange units, so we don't want to really interpret these numbers too quickly. And then for the salary data, instead of VAR.P, I want VAR.S. I want the sample variance, because this represents a sample, which I'm told, it's the only way I know that is I'm told that it's a sample. So VAR.S of, I can type in salary, and that gives me my 759, which I got over here. And then lastly, standard deviation. A couple ways I could do it. I could just use the square root function. If I already have the variance, I know that the standard deviation is the square root, SQRT, of the variance. I could do that. Or I could use the built-in function equals STDEV. Again, lots of other kind of standard deviations, but we're using STDEV.P, the function that calculates the standard deviation based on the entire population, as opposed to STDEV.S, estimates standard deviation based on a sample. So I'm going to pick STDEV.P because the Ashley data represents a population. Select my data, end the parentheses, hit enter. And I see I get the same answer, the same 2, which is now in good units. It's back in the units of the original data, the same units that the measures of center are and that the range are in. So if I want to interpret something, I'm probably going to use the standard deviation. The Brandon data, stdev.p, again, population, so do .p. I select the Brandon data, and that gives me 4, which I could have also gotten with the square root function if I already had the variance here. Either way is fine. And then for my salary data, now instead of using SCDV.P for a population, the salary data is a sample. I'm told that, so that's how I know that. I'm going to use .S. STDEV.S, the sample standard deviation of the salary data. And Excel does all of the n versus n-1 stuff internally. We don't need to tell it to do that. We're telling it to do that by picking population versus sample variance standard deviation. We see that we get 27.5 or so. Any questions on this? Anybody want to see anything again or? Okay. All right, so a few just last little things, just kind of a quick overview. We'll discuss the coefficient of variation, a measure of variation related to the standard deviation, the empirical normal rule, the range rule of thumb, and Chebyshev's theorem. I might actually bump this guy above this one. Probably makes a little more sense there. So this is just kind of like the kitchen sink that we need to throw in somewhere, and might as well throw it in here. Okay, so coefficient of variation. This is another measure of variation. It is the standard deviation over the mean, either sigma over mu, or if we're in the context of a sample, we'd say S over X bar. Whatever way, it's the coefficient of variation. If you forget which way it goes, like is it mu over sigma or is it sigma over mu, it's the coefficient of variation. It's a measure of variation, which means that as our other measure of variation gets bigger, our coefficient of variation should get bigger. So sigma has to be on top. Otherwise, if sigma was on the bottom, as sigma gets bigger, our coefficient of variation would get smaller. That doesn't seem reasonable. And actually, if I had understood this in undergrad, I was taking one of the actuarial exams, and one of the times that I was taking one of them, I was right on the cusp of passing. I was one question away from passing, and I got this wrong. I just made a mental flub, and I did mu over sigma instead of sigma over mu, and realized it afterwards. I was like, oh, I can't believe I made that mistake. And then I missed passing by what amounts to likely one question. They don't exactly tell you what the number of questions you need to get right is to pass. They don't tell you which questions you get right, but you can usually like remember the questions and then figure them out afterwards and go onto forums and figure out, what the pass rates were. People will say, I got, this many questions right, and I did or didn't pass. And so you can kind of figure it out. But I was one question away from passing, and because I had a brain fart and flubbed this, I had to retake the actuarial exam. But that's our coefficient of variation. So for instance, let me just bring this Excel sheet back up just for these measures. And the coefficient of variation, as far as I've ever seen, doesn't get a fancy symbol. It's just CV. The coefficient of variation for the Ashley data is the population standard deviation for Ashley over the population mean for Ashley. Or what is that? It's 2 divided by 8, or 0.25. In other words, the standard deviation is 25% as large as the mean. The coefficient of variation for Brandon is standard deviation for Brandon over the mean for Brandon. This is a 2, which is 4 over 8, 0.5. And the coefficient of variation for the salary data is S over X bar. I guess we could write like S sub S over X bar sub S, but since there's only one sample that we're dealing with, we'll just write it as S over X bar. That is what? 27.5 over 42. So we can actually just hit the divided by button. So we get 27.5 over 42. It's about 0.66 or so. So we see that the Brandon data, its standard deviation is about half as large as its mean, and the salary data, its standard deviation is about 2/3 as large as its mean. One of the super nice things about the coefficient of variation is that it is unitless. Remember that my standard deviation has the same units as the mean. So in other words, 2 returns per day over 8 returns per day, my units divide out, and this is unitless. It's just a multiplicative factor, 0.25. Same with this one, right? Here we have thousands of dollars on top from the standard deviation, thousands of dollars on the bottom from the mean. They divide out. This 0.66 also unitless. My coefficient of variation is always unitless. Oftentimes when you see the word coefficient, that's a unitless quantity. Like I'm pretty sure the coefficient of friction is unitless. So there are things like, coefficient of thermal expansion, things like that. So if you see coefficient of, that often relates to a unitless quantity. I'm no physicist, so don't go telling Professor Farina on me if I got that wrong. But mathematicians despise units usually. But units can be very helpful. If for no other reason than stirring up debate online about whether imperial or metric is better. So, but yeah, so coefficient of variation is unitless. One nice thing about a unitless quantity is by dividing by the mean, we've scaled out the explicit unit, say like returns per day or thousands of dollars. We've also kind of like scaled out the implicit size of the problem, right? Like if I was measuring in just dollars, 27,500 over 42,000, like these numbers are just bigger numbers than 27.5 over 42. I've also kind of scaled out the general kind of size of the problem. The mean is going to be kind of roughly in the center of the data. It's going to represent kind of the size of a typical data point or the size of the data overall. And I've scaled out that size factor as well, that kind of implicit unit of just size. So if I want to say, well, between the Ashley and Brandon data, which one's more variable, I can probably just look at standard deviation directly. Because they have a similar context, their size is similar, and they have the same unit, I can look at 2 returns per day for Ashley versus 4 returns per day for Brandon. That's a sensible unit. It's the same unit. It's the same context. Brandon's data is about twice as variable as Ashley's. Probably a fair conclusion. But if I want to compare them to the salary data and I want to say which of these three data sets is the more variable, well, now I've got a problem. I've got number one, an explicit unit difference. I don't want to just compare 27.5 to 4 and 2 because of the units explicitly not matching. But there's also kind of an implicit difference that, like, well, is the variation in the salary data, is this number being larger, 27.5 being larger than 4 or 2, just due to the way that I'm measuring things, right? If I measured Ashley and Brandon's performance as in like number of tenths of returns per day for whatever reason, you know, then Ashley's standard deviation would be like 20 tenths of returns per day, and Brandon's would be like 40 tenths of returns per day. You know, maybe an average return is 10 pages or something like that, and each page is what we're counting or whatever. So if I change the way that I count things, the kind of implicit unit can be different too. But this coefficient of variation scales out that implicit difference in how I choose to measure the thing that I'm interested in. So I can compare these more readily and I can say, okay, it seems like Brandon's data is about twice as variable as Ashley's data. And it seems like the salary data is a little more than twice, maybe 2.5 times as variable as Ashley's data. Or, you know, a little bit more variable than Brandon's data, maybe 25% more variable than Brandon's data. Any questions on this? So unitless quantities are nice. They're nice to work with. The range rule of thumb, this isn't a particularly accurate rule, but a rule of thumb, also sometimes called a heuristic, is basically a quick and dirty way to get an answer that has a lot of caveats to it. So I can get an answer, I can do it quickly, but it might not be such a great answer. There might be a lot of edge cases and corner cases where that answer is flat out terrible. But the range rule of thumb is that the range or the swath of the real line that the entire data set covers is about 4 standard deviations. This is an idea that, you know, kind of is used across statistics in a couple of different places. And this range rule of thumb where, you know, the size, the breadth, let's say, of a data set is about 4 standard deviations is kind of a very rough idea. Now, of course, the larger your sample, the more likely it is you're going to get an occasional data point that's kind of pretty far from the mean, and the more likely it is you're going to get an outlier here or there. So the larger your sample, you know, the range is always looking at the extremes. So as you increase your sample size, your range is going to tend to increase over time. Not over time, but over the sense of increasing the sample size. So again, some caveats here, but like if I had to estimate, well, let's come over here. If I had to estimate Ashley's range based on her standard deviation, 4 times the standard deviation, 4 times 2 is 8. That's, you know, maybe roughly in line with 6. 4 fours are 16, maybe, I don't know, roughly in line with 11. I mean, it's the same order of magnitude. I guess that's something. You know, 4 times 27, call it 4 times 25 is 100, maybe like kind of in the same ballpark in terms of order of magnitude of 75, right? So, I mean, not a great, not a hugely reliable and very accurate estimator, but for as difficult as it is to actually compute standard deviation, if I can say that a standard deviation is about a quarter of the range, if that can get me in the right order of magnitude anyway, maybe that's something. Personally, I don't see, I think aside from a couple of philosophical notes on this, I don't see much real use for this, but that is the range rule of thumb, that the range is about 4 standard deviations, or that the standard deviation is about a quarter of the range. Okay, so two last ideas. The empirical normal rule, or sometimes called just the 68, 95, 99.7 rule after these three numbers down here, says the following. It says if we have a data set, if it's approximately bell-shaped, what do we mean there? Take the data set, put it into a frequency distribution, maybe a group frequency distribution if you need, get a histogram for it, and is that histogram, does it have a peak, tail off to the sides, roughly symmetric about the peak? If the data set's approximately bell-shaped, then we can say that about 68% of the data points have a value that's in what was within one standard deviation of the mean. In other words, have a value that's in the interval, say x bar minus s to x bar plus s. That's what it means to be within one standard deviation of the mean, from the mean minus one standard deviation up to the mean plus one standard deviation. About 68% of our data points will have a value that's in this interval. About 95% of our data points will have a value within two standard deviations of the mean. So that's x bar minus two standard deviations up to x bar plus two standard deviations. And approximately 99.7% of the data points will have a value within three standard deviations, x bar minus 3s to x bar plus 3s. So if I imagine that I have my data here, let's make some data that are approximately bell-shaped. So symmetric, peak in the middle, tails off to the sides. If I have a mean, x bar, and a standard deviation, what is a standard deviation anyway? It's kind of like a measure of breadth on the real line. So I'm going to represent maybe standard deviation by like this. So this might be x bar plus s. This might be x bar plus 2s. And this might be x bar plus 3s. This might be x bar minus s, x bar minus 2s, and x bar minus 3s, let's say. And if I look at this interval within one standard deviation of the mean, I'm saying if I count the number of data points that fall in this interval, number of data points with a value in this interval, divided by the total number of data points in the sample, that proportion should be about 68%. If I do the same for two standard deviations, count the number of data points that have value within that interval, two standard deviations of the mean, divide by n the total number of data points in the sample, that should be about 95%, and then about 99.7% for three standard deviations. We could also look at this the opposite way and say that only about 1/3 of the data points will be what we call one sigma events, more than one standard deviation away from the mean. About 1/20th, or about 5% of the data points, will be more than two standard deviations away from the mean. And about one data point out of 300 on average will be more than three standard deviations away from the mean. So this maybe gives a little bit more credence to our range rule of thumb, especially when we have approximately bell-shaped data and we don't have a ton of data points, right? It should be quite rare to get a data point with a value more than three standard deviations away from the mean, and we'd expect to get a data point with a value more than two standard deviations away from the mean only about 1 out of 20 times. So that's the empirical normal rule. And then the last idea for today, and as an aside, we'll see what amounts to a proof of the empirical normal rule in chapter 6. So proof, so to speak, in chapter 6. Then the last idea in section 3.2, we don't have time to start 3.3, so we'll cut it after this. And this is Chebyshev's theorem. The proof to follow, I don't remember if I usually do it after chapter 4 or after chapter 5. Chapter 4 or 5. We worked through a couple proofs of some foundational important ideas, but it really helps to have a little bit more structure and a little bit more notation built up to make these proofs just more palatable. Otherwise, it's just a ton of writing and a ton of plus dot 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 plus kind of deals. So we'll wait until we have a little bit more structure, a little bit more mathematical structure and notation built up to prove Chebyshev's theorem. It is a quite important result theoretically. So where the empirical normal rule says something about data sets that are approximately bell-shaped, we have this very important caveat. Chebyshev's theorem applies to any data set. So this is true no matter what kind of crazy data set you come up with. It's true based on the mathematical definitions of the mean and the standard deviation. As an aside, there's like 30 different ways to spell Chebyshev's name. It's a Russian guy, lived in the 1800s, great mathematician. But obviously his name was written in Cyrillic and pronounced in Old Russian. So how you want to pronounce his name or transliterate his name it's almost, almost a crapshoot if you agree with somebody else. But, I think this is probably a fairly accurate representation. Some people will translate it with a V at the end. Some people translate the beginning CH as TCH, like Tchaikovsky. That's the same Cyrillic letter. So, there's a bunch of different ways to translate it. So you'll see his name written all kinds of different ways. I don't know which way our book transliterates it. And as a little aside on him, his first name is Pafnuti. So like probably the coolest first name of any mathematician, Pafnuti Chebyshev. So, and Chebyshev's theorem says for any data set, no restrictions on the data set, the proportion of data points whose values fall within k-standard deviations of the mean, so like up here, 68% was the proportion that fell within one standard deviation of the mean, 95% was the proportion that fell within two standard deviations of the mean. So similar result as up here, except that we removed the constraint on the type of data set. For any data set, the proportion of data points whose values fall within k-standard deviations of the mean is at least 1 minus 1 over k squared for k bigger than 1. Or in other words, another way of saying this is that less than 1 over k squared proportion of the data points have a value that's more than k-standard deviations from the mean. So let's look at some different values for k, and then let's look at 1 minus 1 over k squared, the proportion of data points that fall within k standard deviations of the mean. So we'll pick like, let's say k equals 2, 3, and 4. So for k equals 2, 1 minus 1 over 2 squared, that's 1 minus 1 over 4, that is 75%. So you see, if we have the constraint of a bell-shaped distribution, we actually get 95% of the data points being within two standard deviations of the mean. If we loosen that restriction and say we don't know anything about the data set, we can only kind of guarantee that 75% of the data points, not 95%, are within two standard deviations of the mean. For k equals 3, 1 minus 1 over 3 squared, that's 1 minus 1/9, or somewhere about 89%. So we can guarantee with essentially mathematical certainty, plus or minus round off error, that 89% of our data points are within 3 standard deviations of the mean. If we have the additional constraint that we know the data set's approximately bell-shaped, we can do a lot better than that. 99.7% are within 3 standard deviations. But we can construct data sets that have only 89% of the data points within 3 standard deviations of the mean. And then for k equals 4, 1 minus 1 over 4 squared, 1 minus 1 over 16. Let's come over to the calculator and do this. So we have 1 minus 1 over 16, and that gives me 93.75%. So I have about 94% of the data points are guaranteed to be within 4 standard deviations of the mean. Right. Again, if I can impose normality or bell-shaped on this, the 4 standard deviation value is something like, 1 in 30,000 or something like that, will be more than 4 standard deviations away. So we can do a lot better than Chebyshev's estimates if we know the data set is bell-shaped. In bell-shaped data, we're very unlikely to have outliers that have large outliers. But not every data set is bell-shaped. In fact, some data sets can be, shaped in a way that you approach these numbers. So Chebyshev's theorem is a guarantee for any data set, and because of that fact, it serves as the basis for some of the other theorems that are more immediately practically applicable that we'll talk about. And that's because it serves for any data set. Okay, so any questions on any of this?
I
All
had
right.
a I had
Yeah.
a quick question. Is there a way to find the coefficient of variation in Excel?
So I don't think there, oh yeah, okay, we didn't do that, but I don't think there's a like coefficient of variation function, but we can compute the standard deviation and we can compute the mean and then just take their ratio. So I could either, if I have them computed already, I can just reference those 2 cells, or I could do the standard deviation divided by the mean and get it that way. Yeah, good question though.
Thank you.
Yeah, sure. And I just realized I forgot to mention my, I'll throw this quote of the day on the next time, but there was an example that I thought was good to bring up in stats that I saw over the last couple of days. I like arguing with people on social media because it shows you a lot more of the breadth of different ideas that are out there and different thoughts and things that people have. And in a discussion regarding like affordability of housing and all that kind of stuff, somebody made a statement, and I'm not going to say my opinion on the statement or what the context was or anything, but part of his support for his argument was that the average number of hours worked over the past 3 decades has increased. Now, I don't know what the source of this is. I don't know whether it is a correct interpretation or not, but let's suppose that the source is valid and that the interpretation is accurate. One thing that, if we look at over the span of 3 decades, we talked a little bit before about issues in time series over long periods of time. And one thing that occurred to me, again, does this explain all of the change or not? I don't know. So the details are still, still in question. But one thing that occurred to me was, well, 30 years ago, there were a lot of women who were stay-at-home moms, right? So they were really doing work, but it just wasn't counted in a lot of the economic data from the time. It was a little bit of a detection bias, well, a lot of a detection bias, really. These days, there aren't as many stay-at-home moms. Moms tend to work more in the workforce where their work is counted, or at least more easily counted or more reliably counted. So those, 40 or 50 hours they were putting in at home and were not counted in a lot of economic data in the past are now being counted, and the kids are going to daycare. So, each kid is maybe 4 or 5 hours a week on average for, a daycare worker. So that's being counted as well now. So is this, even if we suppose that the numbers do show this and that the source is reliable and all of that, since we're dealing with, 30 years of time elapsed, are we really comparing apples to apples, or are our data collection methods and what we're actually counting, is it actually what we intend to count, or what we intend to compare the average number of hours worked kind of per person nationwide today versus 30 years ago? So it was just an interesting example that came up that I figured I would mention. But okay, so that finishes us up for today. I will stop the recording and close us.